Okay, so if you remember, the last thing we did was we were looking at a system which was not isolated. So its energy value is not fixed. Initially, we looked at systems in which the energy was fixed, and we said that, okay, so all the microstates having the same energy should have the same probability, and we defined this quantity omega, which was the number of microstates, and then the entropy was defined as the Boltzmann constant times the logarithm of this. And once we have the entropy, we can determine all the other microscopic thermodynamic properties of the system. The second type of system we looked at was if the system doesn't have a fixed energy. It can have any energy whatsoever. And such systems exist, for example, if you look at a reservoir and your system, or in fact in practice, in everyday life, everything is more or less like this. Everything is in contact with the atmosphere, and which acts like a reservoir at fixed temperature, and so basically they can exchange energy, our system and the reservoir. We looked at the question of what is the probability that not the reservoir, sorry, that is my system. We looked at, we could still use the concepts of canonical, microcanonical ensemble, treating the combined system as isolated. And then we asked the question, what is the probability that my system will be in a state R with the energy, in a microstate R with an energy ER? And we drive this probability using various approaches. One of them was this treating the combined system as a microcanonical ensemble, creating a microcanonical ensemble of that combined system. And then we had seen that the probability of the state R was proportional to e to power minus beta ER. Z being our proportionality normalization constant. And beta just turned out to be 1 over the kT. Will turn out to be 1 over kT. Another approach we had was we looked at the ensemble of our system where the energy is not fixed. It can have any energy from 0 up to infinity. And then we looked at the possible distributions that my ensemble could have, and we looked at the most probable distribution, and the most probable distribution still had the same probability for my single state, for my single system. And then we looked at the averages. If you remember, we looked at the this turned out to be most probable distribution of microstates in my ensemble. And also, it also turned out to be the average distribution of the microstates in my ensemble. So basically, there is no fluctuation around that one. So that was our microcanonical ensemble. And that is where we had left. We didn't yet discuss, okay, so we have the probabilities, what now? How do we relate that to our thermodynamic properties? So that is what we will be discussing today. So any questions on what we had done up to now? Again, I repeat, this PR is the probability that my system will be in the state R with an energy ER. Now let's look at the average energy. This basically determines what beta should be. So remember, when we were looking at treating this system in the ensemble theory, we imposed two constraints. One of them was the total sum of the copies in my ensemble in a microstate R should be equal to the total copies in my ensemble, which eventually we took to infinity, and then the average energy of the copies in my ensemble, which is ER and R, divided by the total number. This should be equal to U. These were the two constraints. And actually in this ensemble theory, the parameter beta turned out to be just a Lagrange multiplier. And that Lagrange multiplier is fixed by this requirement, that the U is sum over R, ER, PR. This fixes what beta should be. And this is equal to sum over r ER e to power minus beta ER divided by sum over r e to power minus beta ER. Now, just a word of caution. Now, today we will be dealing with various sums over states and sums over energies. So this is a sum over my states. Different states can have different energy, but I'm counting them as different terms in my sum. Different states can have the same energy, still they are different states and hence different terms in my sum. And later on, I will convert this sum over states to sum over energies, and then we will have a different sum. Now, we had this u, we can also write in the form, well, this ER, let me just take the derivative of this exponent. When I take the derivative with respect to beta of this exponent, I just obtain there is a minus ER, which is cancelled by this minus sign. So basically, u can also be written in this form, which is minus the derivative with respect to beta of logarithm of, well, in the book, instead of the partition function, he uses Qn. This is partition function. Or sum over states. Now keep in mind that here u is a function of beta, which will turn out to be the temperature, and volume, and the number of particles. Well, when you look at the explicit expression over here, the dependence on beta is explicit. The dependence on V and N are implicit in the allowed values of the energy. So if you look at the single particle energy eigenvalues, single particle energy eigenvalues depend on the volume of the system that they are confined in. And the number of particles obviously changes the total energy of my system. Now let's remember what this equation looks like in terms of the thermodynamic potentials that we had discussed. You see, if you remember the first law of thermodynamics, we had the U, the was equal to TdS minus PdV plus mu dN. But I don't want S as my variable. I have the beta, which basically turns out to be temperature, will turn out to be temperature. So du minus Ts is minus S dt minus PdV plus mu dN. This U minus Ts, in the book it is denoted by A, the Helmholtz free energy. So dA is equal to minus S dt minus PdV plus mu dN. Now let's see, in terms of A, U is just A plus Ts. S is just minus dA by dt. So this is equal to A minus T dA by dt. This is our U. Which, by the way, I can also write as derivative with respect to temperature of A over T times T squared minus T squared. You see, if you take that derivative, I have the derivative of A divided by T multiplied by minus T squared just gives me minus T times the derivative of A. Then I have the other term A times the derivative of 1 over t, which is minus 1 over t squared. So here I have this equality. But this is also the same thing as derivative with respect to 1 over t of a over t. And if you remember our previous expression, in terms of the partition function, u is just minus the derivative with respect to beta, or the derivative with respect to beta of minus the logarithm of q of n. And keep in mind that in all these derivatives, here it's kind of obvious that when I'm taking this derivative, I'm keeping v and n constant. So in these derivatives, v and n is constant. And similarly, if you go back to our previous expression, here I'm taking derivative with respect to beta. I'm not changing the energy values. But to keep the energy values, energy eigenvalues the same, I have to keep the n and v constant, because changing them would just change the energy eigenvalues. So in this derivative also, I'm just, okay, here v and n are constant, here also v and n are constant. So if you just compare, the obvious identification would be just beta should be equal to proportional to 1 over t with some proportionality constant. Let's just call it k. Eventually it will turn out to be Boltzmann constant. And then minus the logarithm of qn turns out to be a over the same constant times t. Or this Helmholtz free energy of my system is minus kt times logarithm of qn. Now we have the connection between all these between the partition function, this statistical description, and our thermodynamic potentials, A. And remember, dA is minus SDT minus PdV plus mu dN. So once you have A, you can calculate everything you want. Now let's see how this looks like for a classical system. You see, we had already written Qn in the form sum over states e to power minus beta ER. Well, this is implied for a quantum mechanical system. We have discrete states, discrete microstates, but we can just straight away convert this into convert this to a classical expression valid for a classical expression. We had already discussed a bit the partition function for n particles will be, now for a classical system, the sum over states just becomes an integral over phase space. Well, of course, in phase space, not every point corresponds to a microstate. Each microstate corresponds to a volume of 2 pi h bar to the power 3n. And if we are looking at identical particles, indistinguishable particles, we also have this 1 over n factorial of e to power minus beta. Of course, the energy of my system is now h, p, and q. So this is my partition function for a classical system. Well, let us look at an application. Again, our simple system would be the ideal gas. We had already discussed the ideal gas for in the microcanonical ensemble. We can just discuss the same thing in the canonical ensemble. Well, the Hamiltonian of the system is just sum over all particles, pi squared divided by 2m. So the partition function is 1 over n factorial d3 p d3 q divided by 2 pi h bar to the power 3n e to the power minus beta sum over all the particles of pi squared divided by 2m. Well, this I can also write, let me just slightly change its form. Product over all the particles of e to the power minus beta, their momentum squared divided by 2m. Which I can also write in this form. You see, I can just convert it into n independent integrals multiplied. So basically all the particles, the momentum of the particles are independent of each other, so I can just separate this integral into n independent integrals. And if you look at each term in the parentheses, this is nothing but the partition function of a single particle. This is just q1. So for n particles, the partition function is 1 over n factorial q1 to the power n. By the way, up to this point, I didn't even use the explicit form of the Hamiltonian for a single particle. The only thing I used was the Hamiltonian of the combined system is just sum over Hamiltonians corresponding to each particle separately. That is the only thing I used. So this, the particles, and this is valid as long as my particles are not interacting with each other. So this expression we have over here is valid for a gas made of non-interacting particles. Even they can even be molecules. They can have their internal degrees of freedom, etc. So this expression will still be valid. So if we can calculate, if we can ignore the interaction between different molecules, if we can calculate the partition function for a single molecule, then we can obtain the partition function for n molecules using this expression. Now our q1 is d cubed p d cubed q divided by 2 pi h bar cube e to the power minus beta p squared over 2m. Well, the q integral, the integral over positions, just gives me the volume of my system. The p integral just will give me a pi over beta over 2m. Each one will bring the square root of that expression. I have 3 of them, divided by 2 pi h bar cube. Or q1 is equal to v 2m pi over beta 4 pi squared h bar to the power 6. Now h bar squared all to the power 3/2. Pi's cancel, 2's cancel. This is v over v times m over 2 pi beta h bar squared to the power 3/2. So this is my partition function for a single particle. Then the n particle partition function is just this raised to the nth power eventually we need the Helmholtz free energy, which is minus kT, or let's say minus kT times n times logarithm of q1 plus kT times n times logarithm of n, approximately. I just use a Stirling's approximation, which we had discussed, that is precise enough for large enough n. And then we know what Q1 is, minus kT and logarithm of v, m over 2 pi beta, h bar squared. Well, let me just rewrite the beta also. Beta k times d, t, h bar squared to the power 3 halves, plus n kT logarithm of n. Well, okay, you can, if you like, you can even simplify it further. Now, what is the, let's say, the pressure? So you see, up to now we said that K is a proportionality constant, but we didn't really say that it's the Boltzmann constant. Let's look at the pressure. We know that the pressure of the system is minus the derivative of the Helmholtz free energy with respect to volume, keeping N and T constant. This is minus the derivative with respect to volume. If I just pick up the V-dependent part of the Helmholtz free energy, that is minus n kT logarithm of V plus other terms. Well, the other terms do not depend on V, so I don't really care about them. So this is n kT over V. So it's actually the K over here, PV, is equal to nKT, which is the ideal gas law. But in the ideal gas law, the constant appearing over here is the Boltzmann's constant. So in the definition of, in the relation between A and the partition function, that proportionality constant that we had put, K, is actually the Boltzmann's constant. And, well, if you like, you can calculate the entropy just by taking the derivative. S is minus dA by dt at constant volume and the number of particles, etc. Well, okay, so the relation between the free energy and to study the relation, whether our equality is valid or not, we can also look at the pressure. What is the pressure in terms of the probabilities? The average pressure of my system. Well, the average pressure would be nothing but the average of ER by dV. Of course, in this derivative, keeping the n constant. You see, imagine your system in a given microstate. If you change the volume, the energy of the system will change. And the change in the energy will be basically related with the work that you do on the system. And the work you do on the system will be basically the integral of the pressure that you exert times the change in the volume. So basically, the pressure you can write as the change in the energy divided by the change in the volume for a given microstate, not necessarily an average. Well, the average pressure will be just the average of this ratio. But there is one assumption that we are actually making over here. We are assuming that R is not changing as we are changing the volume. So my system is not the microstate of my system doesn't really changing. Well, it's not changing in the sense that the microstate will depend on V. But for a given volume, there is let's say the ground state for a given volume. If my system initially is in the ground state for the given volume, it will still stay in the ground state for the given volume. In that sense, R is not changing. Or if it's, let's say, in the fifth excited state, as I'm changing my volume, it will still stay in the fifth excited state corresponding to the given volume. That's another.
Keeping the temperature constant in that case?
Well, you see, the ER does not depend on temperature. It's for a given microstate. What depends on the temperature is the probability of that microstate. So this derivative over here, derivative of ER, there's no temperature dependency there anyway. That's why I only wrote at constant n. So that averaging is just, sorry, here I have a minus the derivative of ER with respect to V, e to power minus beta ER, divided by sum over R e to power minus beta ER. Now what I will do now is take that derivative with respect to volume out of my summation. Minus derivative with respect to V of this one. Now, of course, we should take the derivative as we keep n constant and also beta constant, or the temperature constant. Because in this summation depends on temperature. ER doesn't depend on temperature. Which is 1 over Qn minus the derivative with respect to the volume of n and t. Well, that summation is just u, Qn times u. This is the pressure of my system. This is 1 over Qn minus the derivative with respect to V of n and t of Qn with respect to u plus u, minus the derivative of u with respect to V. Qn's just cancel. Well, let's see, this is minus the derivative with respect to V of logarithm of Q times U minus the derivative of U with respect to V or let me just okay, so this is the derivative of Q here I have Qn times 1 over Qn. So P is minus the derivative of, did I make some sign mistake somewhere? No, this is all the minuses. Okay, p is this one. Minus the derivative with respect to v of the logarithm of q minus qn minus u. This we already said that is minus kt times the logarithm of a. So p minus kt times a over kt. And a was u minus okay, now let's just keep. Now what I'm trying to show is this equal to derivative minus the derivative of a with respect to v? That is what we would like to show. Because in thermodynamics, that's the P should be expressed in terms of A in that form.
By the way, why did you write minus U instead of minus du over dv? Oh, in the first line of the second page.
No, this is du over dv, you're right.
And we have u in the first term outside the brackets. Yeah, we should have.
Yes, you're right. And we are keeping n and t constant. So this is equal to u times kt times the derivative of a with respect to v minus du by dv. Did we make some mistake somewhere? You see, the first line is correct. Okay, here is fine. I take the volume derivative out. This is what remains. This is just Qn times U divided by Qn. I just separated the derivative of this one times U plus or minus Qn times the derivative of U with respect to V at constant n and t. This is A over kt. So there I have one mistake at least.
Kt should be anyway.
Okay. So do we have this equality? How can we simplify this? A was, or U is A plus TS. So let's try to simplify it. A plus TS, 1 over KT, dA by dV minus d over dV at constant n and t, A plus Ts. One over kt, A times dA by dV plus S over K dA by dV minus dA by dV.
By the way, it's better to keep U as,
U.
in the first term we have A plus SD. It's already U. So we don't need to...
Well, you see, this expression doesn't depend on U. That's why I try to replace U by A here. But, well, let's see. Let me do one thing, something else. What is du by dv? You see, du was TdS minus PdV plus mu dN. So du by dV at constant n and t is t times ds by dv minus p. Now ds by dv should be dp by dt.
I think you can insert this du over dv with keeping this constant nt is equal to t blah blah something. We can put this relation into first line.
Okay.
And then I guess we will get the result when a is equal to u plus tds something, I guess. No, sorry, u is equal to a plus tds. ts, sorry.
Let me cheat.
Okay.
Okay, so this is the pressure. PdV is minus du. Well, let me leave that derivation aside. I mean, there should be a way to obtain it, but I don't see how now.
I think you have already done this.
We have.
All we need to do is, instead of du over dv, we have to put this relation into the last line here. Minus du over dv. Yeah,
So you are saying that pressure should be U over kT, dA over dV, and T minus, instead of du over dV, I put T dP by dt plus P.
No, not that one.
Which one?
The relation above. T ds over dv minus P.
You see here?
No, it was correct. Just yeah, it's okay. Yeah, instead of minus t dp dt, we can write the relation in the first line. T
plus T or minus T
ds over dv
plus P. This one. You see, there is this Tn which is just makes things more complicated, because if I try to sum them, I just end up having T squared, the first two terms.
But you said A is equal to, what was that? You're right, A or U was equal to A. Then du.
Anyway, let me just leave this.
Okay.
It should be correct, but I don't see the derivation now. Rather, we can discuss it later on. Now, and one thing I didn't like in this derivation up to this point is that what I would like to show is that the pressure is actually equal to this one without using the, when A is equal to minus kT logarithm of Q, we should be able to write P in this form without using the thermodynamic relationships, if possible. Because then we can claim that P and A defined in this way satisfies the thermodynamic relations we have. So using this one is already I don't really like, because I would rather avoid using all thermodynamic relationships. Anyway, we can discuss it later on. Now, before I started this derivation, if you remember, I was saying that P is okay. It's equal to DER by dV minus times PR, which I was saying that, okay, we are assuming here that we are changing the volume such that we are not changing the probability distribution. Well, in thermodynamics, that basically corresponds to what we call the quasi-stationary change. So we are changing the system very, very slightly. In quantum mechanics, that corresponds to what we call an adiabatic transformation. Your system, you are changing the system sufficiently slowly that there are no transitions between various states. It's just a given state. The system, if it's in a given state, it stays in that state for the corresponding new values of your parameters. So basically, this is where, in the thermodynamics, when we were saying that, okay, let's look at this very small change, very slow change, well, this is where that enters in the statistical picture. The probabilities should still stay the same. And then, of course, as we had just seen in the book, P times dV is just minus PR times DER, which is minus d of the change in the energy of the system, or minus du. So this is basically our relation of this one relation between the thermodynamic properties and our statistical description. Now let's look at something else. Logarithm of PR, the average of that one. Now why? Well, we will see in a moment. This is equal to the average of logarithm of e to power minus beta r, beta ER, divided by Qn, which is minus beta, the average of ER, minus logarithm of Qn. Well, Qn is just the constant, so its average is also just itself. minus beta u minus logarithm of qn. Or u over kt minus, you see qn was minus a over kt. So this is equal to a minus u over kt. Or keep in mind, a, we had defined a as u plus ts. Minus u divided by kt, this is s over k. Or you see s just turns out to be k times logarithm of pr. Now this expression, this final expression is also sometimes called, especially in information theory, is the Shannon's entropy. Okay, so what does it mean? Why is it related to information theory? How the relation comes about? You say, what is PR? Well, it's some probability. It can be between 0 and 1. So let's say if we know that the system is in a given specific state, we know that the probability of that state is 1, the other states are 0. So if we know that, you see, the logarithm of 0 seems to diverge, but keep in mind that probability is defined in this form, k times that average logarithm of PR times PR over R. If PR is 0, logarithm of PR times PR is 0. So it doesn't diverge. The limit is finite. So if a system is if we know that the system is some particular microstate, then this S is basically 0. Because if PR is either 0 or 1 for that particular state, if PR is 0, there is no contribution to the sum. If PR is 1, logarithm of 1 is 0, so this is 0. So we know everything about the system. So that's kind of the maximum knowledge we can have, maximum information we can have. The other extreme would be if, let's say, there are many states that have a given, we don't know anything about the system. So in that sense, this S just increases. It starts from 0 if we know everything about the system, and it increases if we know very little about the system.
Well, it seems like it will always negative, right? How come I couldn't...
No, hold on.
There should be a minus sign somewhere.
Yes. There is a minus sign over here.
Should be over minus sign, I guess.
Minus beta ER minus the logarithm of Qn minus beta U minus U over KT minus the logarithm of Qn is minus A over KT. So this is A minus U, A is U minus TS. Okay.
By the way, when PR goes to 0, is it 0 or minus infinity?
0, because you see, x times logarithm of x. In this sense, it is 0. This is 0. Now, in fact, this definition of entropy is, although we kind of have seen it in the canonical ensemble, that's also valid in the microcanonical ensemble. How to see that? Well, what we did in the microcanonical ensemble was that there are this many states that the system can be in, and we said that all the microstates are equally probable, so the probability of one of those microstates is just 1 over q of omega of E. So with this probability, S is minus k. Well, let me just, S is minus k times logarithm of PR, average, which is plus k times the average of logarithm of omega of E. Well, omega E is constant in the microcanonical ensemble. S is just k times logarithm of omega of E. In fact, if you can also do an exercise. Let's do an exercise. Let's say S is minus k logarithm of PR. Yes, in the microcanonical ensemble, we don't know anything about the system, so we are just assuming that the simplest choice will be PR is the same for everything. In the canonical ensemble, well, we still have this sum over PR should be equal to 1. And PR times ER, this is equal to E. We have these two constraints. And what is the maximum possible value of possible, which probability distribution makes the entropy a maximum? So you can just look at the variation, delta S is equal to 0, subject to these constraints. And you again discover that for this condition, PR has to be e to power minus beta ER, proportional to. So basically, this probability distribution maximizes the entropy, subject to the given constraints. So in fact, actually, if you want to find the probability distribution of any given system, subject to things that you already know. For example, in the canonical ensemble, we don't know what the energy is, but we know the average energy. We are fixing the average energy to be, U. If you know something else about the system, that's an additional constraint on your system. Just add the third constraint. If you know something else about your system, add it as a fourth constraint. And if you maximize the entropy, that will give you the probability distribution for your system. Now let's look at one more thing, and then we can give a break. So you see, we have these two ensembles, microcanonical ensemble and the canonical ensemble. But we had looked at, for example, one case, the ideal gas, and we have seen that PV is equal to NKT in both canonical and microcanonical ensemble. And although we didn't really discuss it, U is equal to 3 over 2 NKT, both in the canonical and microcanonical ensemble. So basically, to study the ideal gas, if you want to study an isolated ideal gas, you can use the canonical and the microcanonical ensemble. If you are studying an ideal gas in contact with a heat reservoir, you can use the canonical ensemble or the microcanonical ensemble. So although when we were talking about them, when we were looking at the microcanonical ensemble, we said, let's assume our system is isolated so that the energy is fixed. In the canonical ensemble, we said, let's consider a system which is in contact with a heat reservoir, so its energy is not fixed. But this separation is kind of superficial when we look at equilibrium properties. Because in equilibrium, basically, the properties of the system does not change. You see, if you take your system in contact with a heat reservoir, if you look at its energy, it will not change in time. So it shouldn't really make any difference whether it's in contact with your reservoir or isolated. That is whether you are using the canonical ensemble or the microcanonical ensemble. So how does it come up with in this description? So let's see. Let's look at, let's start with our Qn. Sum over all stays e to power minus beta ER. And we were looking at the average of anything will be basically sum over R or let's look at the classically, d omega, the volume, times F. Well, there are quite a number of observables which depend only on the energy, like the momentum. Magnitude of the momentum depends only on the energy, for example. So that's why I just assume that this observable F depends only on the energy. But then you see, I can kind of change my integration variable. Rather than integrating over all points, or let's say rather than sum over all states, I can just sum over all energies. But for a given energy, there are many microstates. Let's call it GR of E. So here I define this GR of E to be the number of well, there are no R. Yes, number of microstates having energy E. So the average of F will be E times e to power minus beta E G of E. Now, before I was talking about the probability for my system to be in one microstate. Now I can talk about the probability that my system will have the energy E. This will be G of E times e to power minus beta E. Now, if you remember in the microcanonical ensemble, we had already studied what the number of microstates corresponding to a given energy, and we had seen that it increases really fast. So as a function of E, now GE increases very fast. This is G of E, much faster than this one. If you look at the exponential, it decreases very fast. Well, if you just multiply them, the product will start increasing due to the increase in G of E, but then it will start decreasing due to the suppression by the exponential. So the product will basically have such a dependence. And then we have this most probable energy value. Now, what is that most probable energy value? Well, we basically determine that most probable energy value by taking the derivative of this probability distribution with respect to energy. If we evaluate it at E star, this should be 0. Well, let's say this is G prime at E star times the exponential minus beta G of E times the exponential this should be 0. Or
it should be E star again, right?
E star, yes, everything is G star. So G star, G prime, derivative of G at E star with respect divided by G at E star should be equal to beta. Or T times derivative of the logarithm of G with respect to E evaluated that E is equal to E star, sorry, not T. Should be equal to 1 over T. But you see, G is nothing but the number of microstates having the energy E. That's what we used to call omega when we were dealing with a microcanonical ensemble. So that derivative is, and if you remember in the microcanonical ensemble, we define K times logarithm of G to be the SE. So that relation is just ds over dE. Evaluate that E is equal to E star, should be equal to 1 over T. But this is nothing but the relation we obtain in the microcanonical ensemble. Of course, in the microcanonical ensemble, energy was fixed at a given value, so we evaluated that entropy with respect to energy at that fixed value. In the canonical ensemble, energy is not fixed, but S is still the entropy we define in the microcanonical ensemble. If we take that derivative with respect to E, not at the fixed energy value, there is no fixed energy value, but the most probable energy value is still exactly the same relationship. So basically, the most probable energy value in the canonical ensemble is the energy, corresponds to the energy in the microcanonical ensemble. Now let's look at one more thing. What about the fluctuations in the energy? You say, what I will claim is that the fluctuations in the energy, it basically goes to 0. So what I would like to calculate is this one. The average of E squared, or let me write it in a slightly different form, E minus U squared average divided by E squared. This should go as 1 over N. This is what I'm going to show now. So this will basically tells me that for in the thermodynamic limit, that is as N is infinitely large or large enough, let's say, there is no fluctuation. So there is no fluctuation, and hence the average energy is equal to the most probable energy, and also basically the energy is fixed. It doesn't even fluctuate. The fluctuations are negligible. So I can treat my system either in the microcanonical, in the canonical ensemble, or the microcanonical ensemble. They will basically yield the same result, because the deviation, the probability of a deviation will be 0. So, do you want to break now, or if you want, we can just prove this and then give a break. Maybe we should give a break now. Okay, let's give a 5-10 minute break, and then we will show this one.
Şu an bunlarda herhangi bir star olacak mı? Son satırda.
Well, let me slightly correct it. You see, what we have actually shown, when we show this one, what we actually show is that for all practical purposes, well, the average of E is U, which is just E star. Because the fluctuations will be negligible. So the average energy will be equal to the most probable value.